Για τραβά να ξέρεις. Το πρώτο.
Το πάτησα.
Κάτω, αριστερά, βρίσκεσαι. Όχι αυτό, πιο κάτω.
Έτσι, παίρνουμε.
Όχι, ναι, σωστά. Που λέει AI Assistant, αυτό τα εκεί που λέει AI Assistant, αριστερά, αυτό πάρα. Αυτό πάρα.
Κάτσε όμως να βάλω αυτό, έτσι.
Όχι, το screen βάλω. Και αυτό πώς να βάλω. Για ρίξε, να δούμε.
Αλλάζει, συνήθως από αυτό έχει κάνω.
Πήγαινε full screen, για. Να χαράσει. Πολύ φως. Χαράσει. Κάνε κλικ από αυτό.
Εντάξει. Προχωράει. Δεν προχωράει όμως.
Κάνει καλύτερα σε screen.
Με το πάνω κάτω, οκ.
Θες μήπως ένα ticker.
Μπορεί.
Τσιπατό έχει ένα USB πάνω, το βάζω χθες.
Αυτό δεν θα φαίνεται όμως στο WebEx,
Θέλω να δείξεις κάτι.
Ναι.
Το ticker για να κάνεις προς πίσω advance. Προς πίσω.
Εντάξει, θα πάω και τα κουμπιά εδώ.
Για να πούμε πώς θα το κλείσουμε στον χρησμό, πόση δηλαδή συζητία ακόμα θα γίνει.
Δεν έχω USB εδώ.
Περισσότερη βεβαιότητα, αυτό το κρίσιμο στοιχείο είναι ότι οι σεισμοί αυτοί που έγιναν και οι τρεις μεγαλύτεροι έχουν πανομοιότυπη τρόπο το βάσιμο του ρίχνοντος και η δουλειά πείσματος με οριζόντια μετατόπιση.
Δεν είναι τα παιδιά μέσα.
Μιλάνε κάποια, μπορεί να
ξέρεις.
Το κλείσατε. Γεια σου, Γιώργο. Καλώς ήρθες.
Είστε φωτογραφίες, τις πειράζεις.
Ναι.
Γεια σου, στο τέλειο.
Είναι φωτογράφος.
Δεν έχω τι δεν έχω φωτογράφεις πάλι. Όλα καλά.
Όλα καλά.
Χαίρεσαι.
Μεγάλη τι γίνεται.
Ξέρω τι κάνεις.
Μια χαρά, Νικολάκη μου. Είσαι.
Έρχεται γραφείο.
Ναι.
Αφορμής τη σοβουλιά σου, θα ξαναπέγει τους άτομους για να μην
Δύο λεπτά ακόμα μας έρχονται.
θα περιμένω πώς.
Κλασικά πήρα το τηλέφωνο. Δεν θα γίνει κάτι.
Αριστερά.
Σε τα ποντίκια.
Ρίξε από κάτω, ναι. Πώς και τι λες, ότι θα χρησιμοποιηθεί ραδιόξο.
Θα μην του αστεία και αυτά που συζητάς. Δεν ξέρω ψάχνει στο περίπτωση, πάρα πολύ.
Δηλαδή κάποια από αυτά δεν έχουν δημοσιευτεί ακόμα.
Αυτά είναι εύκολο.
Δεν υπάρχει κάποιο εμπάργκο.
Υπάρχει. Ποιο όντως υπάρχει. Όταν υπάρχει το εμπάργκο του να θυμηθώ εγώ να κάνω το κλασσικό.
Θυμάμαι, σε θυμίζω εγώ.
Ρίξανε. Και μετά υπάρχει ο Μπάρκοφ στο στέλνο και σου λέω: δες από αυτά που σου φαίνεται και τι θα πω. Και το κλείσει λίγο στο λάδι. Και δεν έδωσε έλεγχο. Και εδώ με τον έντοξο Τατιά. Πώς απασχολεί, για ελληνικά είμαστε...
Η Μαρία και ο Πέτρος θα ήταν στα ελληνικά.
Και η Μαρία στα αγγλικά, ναι.
Στα αγγλικά ο
Η
Πέτρος.
Μαρία δεν πάλι στα ελληνικά. Η Τρέση νομίζω.
Στα αγγλικά. Για το καλό όλων.
Έχουμε συναντηθεί online, είμαστε απλώς να μιλάς, να είσαι μπροστά στο μικρόφωνο.
Νομίζω είναι καλό.
Πού είναι το μικρόφωνο?
Το πάνω του λάπτοπ θα υπάρχει άλλο.
Α, του λάπτοπ. Τότε θα πιάνει μια χαρά.
Ξέρω την ποιότητα του λάπτοπ και αυτό είναι καλό λάπτοπ. Πιάνει πολύ καλά.
Είναι καλό το Berkeley, το λάπτοπ είναι αναλυτικά.
Από το Τέξας είναι.
Berkeley. Λίγο άργο το υπόλοιπες, βασικά. Εντάξει. Είναι ποινική όπως τώρα.
Δεν υπάρχει. Θα κόβεις τέτοια.
Πώς ήθελες, εμάς καταγραφεί. Βάτα από μονός.
Έβαλα σήμερα στο YouTube και είδα την ομιλία που έκανε στο strengthening στο Περιστέρι. Ναι, εσύ, την έχω αναβάσει. Εσύ. Είχε 2 likes, δηλαδή, εγώ κάνω το τρίτο. Είναι όλα αυτά που λες για το παδά, μου άρεσε πάρα πολύ. Και το σεισμό που χωρίζει από εδώ, εσείς από εκεί θα πάτε το σεισμό το μεγαλύτερο.
Ποιος είναι δικά της εθνικής, επί 2, να στρώνει. Έστε, μην δεν αυτό το αλλά κάθομαι κι εγώ, πίσω είναι η ώρα.
Εντάξει.
Πάμε να κάτσω εδώ πίσω. Λοιπόν, κυρίες και κύριοι, είμαστε πολύ χαρούμενοι να έχουμε μαζί μας τον κύριο Κωνσταντινίδη, δόκτωρα Κωνσταντινίδη παρακαλώ, ο οποίος μας ήρθε από το Berkeley, βέβαια από εδώ ξεκίνησε, όχι ψέματα, από το Berkeley ξεκίνησε. Ήρθε εδώ, ξαναπήγε εκεί, έκανε μια βολτούλα από το Καναδά και τελικά κατέληξε στο αγαπημένο μου που φαίνεται να είναι. Πάρα πολύ ωραία. Και θα έχει τη μεγάλη χαρά που μας μιλήσει για ένα σωρό πράγματα περί σεισμικής μονώσεως και μάλιστα δεν της ευθυνής. Και υπάρχει πολύ κόσμο που προσπαθεί να μας πει ότι μα ήδη είναι ευθυνή. Δεν θα παρέσει σε σχέση με όλα τώρα που ανεβαίνουμε. Τέλος πάντων, όπως και να γίνει, χαιρόμαστε που σας έχουμε μαζί μας, αγαπητέ κύριε Κωνσταντινίδη. Και παρακαλώ, δώστε ελεύθερα αγγλικά, ελληνικά, the floor is yours. Θα καταλαβαίνουμε από όλα εμείς.
Εντάξει, αγγλικά καλύτερα, για το καλό όλων, όπως είπα. Thank you everybody for joining us tonight for this presentation. It's my honor and pleasure to be here. You know, some 30 years ago, I was in a fork in my life where I had to make a decision whether I'm going to study here in Greece at NTUA or go to the US. For me, the choice was a little different than most because I was born in the US, and when I graduated high school, the natural course was to move back to the US, and I did that. But you know, I've always thought of NTUA as my parallel universe. If I hadn't gone there, I'd be here. Anyway, what I would like to do today is talk to you about fiber reinforced elastomeric isolators. And the title here, if there are any Stanley Kubrick fans in the audience, but it's motivated by the movie Dr. Strangelove, probably one of the best satires, I think, ever made on screen. And I think it will become obvious why I'm saying how I learned to stop designing or seismically protecting only for the rich. Okay, so the isolators that I'll be talking about today are the product of a broader effort led by my group and others, including Michalis Vasiliou, and Yorgos has done some work in this, to find ways to reduce the cost of seismic isolation and expand its application beyond high importance buildings to more normal occupancy buildings. Now, is the cost of the devices really what governs that? It's not just the cost of devices. There are several things that come into play, but the cost of the devices are a starting point, and it is a significant part of reducing the overall cost of seismic isolation. Now, this might be a little bit, having a hard time advancing here.
Try to click it.
To click that to get the focus.
Huh?
First, you need to click to get the focus and then work. Okay.
Click where?
It's just on the screen. Yes.
Okay. All right. So, at the risk of sounding a little bit pedantic, I don't know if everybody is familiar with the concept of seismic isolation, but I have included a slide or two. I oftentimes give presentations to groups that are not familiar with the concept, and I go on and talk about it without them knowing what I'm talking about. And it only becomes apparent at the end of the presentation. So I don't want to run into that situation. I want to spend just a minute or two talking about what seismic isolation is. So seismic isolation involves the introduction of a horizontally flexible layer, typically at the base of a building, but not necessarily. And the idea here is that when an earthquake comes along, that large horizontal flexibility essentially decouples the motion of the superstructure from the motion of the ground. Okay, so here I'm going to show you a video that illustrates how this works. On the left, you have a seismically isolated building where it moves almost as a rigid body. On the right, you have a fixed base structure that experiences a lot of damage. Okay? I mean, nowadays we tend to use the word ductility a lot, but ductility is really a euphemism for damage. That's what it is. So seismic isolation basically concentrates the deformations in the isolation layer, where you can use specially designed devices that can handle very large deformations or sliding. Okay. Now, from the point of earthquake engineering, what that does is if you look at the response spectrum, essentially introducing that horizontally flexible layer increases the fundamental mode of your structure. It also increases damping a little bit, but that's a secondary thing. Okay. Sometimes I hear people calling isolators dampers. They're not dampers. Seismic isolation is a different thing. Okay. Damping is an additional, an extra thing, a secondary thing, but it's not essential. Okay. Now, all this, of course, happens at the expense of increased displacements, but those displacements are again concentrated at one location where you can deal with them, as opposed to having them distributed throughout the structure and causing damage. Now, this is again part of the introduction. This is just a video of a seismic, I think this is a lead rubber bearing. I just want to give people an idea of how much seismic isolators deform. Okay. So this is a test at UC San Diego. And you see the deformations here in the order of about 300%, I believe. So 300% means that the lateral displacement is 3 times the total height of the rubber. Okay. Now, could steel structures do that? Could reinforced concrete structures do that? No. Okay. All right. Now, I want to talk a little bit about elastomeric isolators because that is the focus of my research, has been for many, many years. And this is the anatomy of a rubber bearing. Let's say if you look at it inside, it consists of layers of rubber and steel plates, thin steel plates, sometimes called shims. And then at the top and the bottom of the bearing, you have these thicker steel plates that are used to connect the isolator to the superstructure and substructure. And I'm going to talk a little bit more about that. Now, the issue with conventional steel reinforced bearings is that they have a lot of steel, okay? And because steel is quite dense compared to rubber, you end up having a device that weighs in the order of 0.75 tons, sometimes up to 1.5 to 2 tons. So they're quite heavy, okay? Now, the concern with the weight is not so much the behavior during an earthquake, but it's the construction, okay? So if you have a device that weighs, a ton or more, and you want to implement it in a low-cost isolation setting, maybe in a developing country, you would need to have lifting equipment. But you can most likely not afford lifting equipment. So kind of that kind of limits already your options. The other thing about steel reinforced elastomeric isolators is that they are manufactured using a very expensive bonding process between the rubber and the steel. And you need to have that because you get these very large tensile stresses that develop as the bearing deforms. And these very large tensile stresses can make the rubber peel from the steel shims, and then your bearing is gone. Okay? That is a very laborious process, and it significantly contributes to the total cost of these devices. Okay? Now keep that in mind because in a second I'm going to come back to this and talk to you about how fiber reinforced elastomeric isolators deal with that problem. Okay, now in terms of cost, a device like this, so this particular device on the left, this is an Andre high damping rubber bearing that was used in an isolated building on campus at Berkeley. This is probably in the order of, I would say maybe nowadays $15,000 to $20,000 per bearing. Okay, and the cheapest you can get in the US is about $10,000 per bearing. Okay, so they're quite expensive considering that you normally have to have a bearing underneath every column in your building. Okay? So significant cost. And the goal of this research in fiber reinforced elastomeric isolator is to find a way to try to reduce these costs. So the idea behind FREIs, fiber reinforced elastomeric isolators, is first to replace the steel reinforcing plates, the shims, with carbon fiber mesh. Okay? Carbon fiber mesh is very light. It's relatively cheap, not everywhere in the world, but in most places. And then also, the goal is to eliminate the top and the bottom steel end plates, which tend to be thick, typically in the order of maybe 3 centimeters thick. So they add a lot of weight and cost. So eliminate those. And there are certain implications associated with that, which I'll talk about. And then the other nice thing is that you could take these bearings and manufacture them in a big sheet, okay, a very large mat, and then just cut them to size according to your desired specifications. You can't really do that easily with steel reinforced bearings, okay? So in terms of savings in weight, just going back to what I was saying earlier, for a steel reinforced elastomeric isolator, you would have to use lifting equipment, okay? So that already eliminates your options in a lot of low-cost developing world settings. On the right, fiber reinforced elastomeric isolators are so light that you can just pick them up, okay? So the lifting equipment here on the right is Professor Jim Kelly. Jim Kelly is the father of seismic isolation. And that's all it takes. Construction worker takes the isolator, places it where it's supposed to be, and you proceed from there. Now, what are the implications of these changes that we have introduced? So I want to talk a little bit about the backbone behavior of elastomeric isolators. So on the left, I have a conventional isolator that is anchored to the top and bottom, to the superstructure and the substructure using anchors. Sometimes we tend to call this configuration bonded. Okay, and that is in contrast to what we have on the right, which is a low-cost application where the isolator is just put in place. Okay, no anchors in this case. It relies on friction to transfer the shear forces. Okay, now this is something that has been contested over the years. How can you rely on friction? But I'll come back to that again later. Okay, we have shape table tests that show that it actually works pretty well. Okay, so what you see here for a conventional isolator, assuming that there are no P delta effects, let's put those aside for now. If you shear it, what you get is just a line. It's just a spring. Okay. Whereas for an unbonded fiber reinforced elastomeric isolator, what happens is as you start shearing it, the top and the bottom corners here roll off the supports. So you start losing some effective shear area. Okay. And that reduction in the area, the shear area, results in this softening behavior. Okay. And as you keep shearing the isolator, what happens eventually is that this face, which was originally vertical, eventually becomes horizontal. Okay, we call that full rollover. And you can still actually keep shearing these bearings without them sliding if they're fiber reinforced elastomeric isolators. They kind of roll up into a ball. Okay, but we call that condition full rollover. And what happens beyond that point is you have a stiffening effect. So you start getting something like this up here. Okay. Now, an attractive feature of this kind of behavior is that it offers these adaptive characteristics. So you can design your isolator to achieve different performance objectives under different earthquake excitations. So you have a design level earthquake, you might want to be around here, where you have effective seismic isolation, relatively low effective stiffness, longer period. But then when you get to larger earthquakes, maybe in that case, you want to limit your displacement. So you want to have a system that kind of stiffens up here. Okay. So sort of to summarize things for now, there are various advantages behind FREIs. One is business of the rollover effect. Okay, you can get adaptive behavior. Now, there is another very important implication behind this rollover deformation. And that is that when you allow the bearing to roll off the supports, you alleviate the high tensile stresses that would develop normally at these corners if these were bonded to the top and the bottom, as they are in conventional isolators. Again, going back to this, it is these high tensile stresses that result in this very expensive manufacturing process. So if you don't have these high tensile stresses, you don't need to have such a fancy manufacturing process. And you can make these bearings for a small fraction, okay, less than an order of magnitude. We're talking about like a bearing like this would be in the hundreds of dollars versus 10,000 or 20,000, okay? And that's for rubber bearings. I mean, let's not talk about sliding bearings. Because just as a parenthesis, I was involved recently in this evaluation of a hospital in San Francisco that was to exhibit very large displacement, 52 inches. 52 inches is something like 1.3 acres. You cannot achieve that with elastomeric bearings. You need to go to sliding bearings. But the cost of the devices was $75,000 each. Okay. All right, so there are various advantages, lower manufacturing and installation costs. There is lower lateral stiffness, which essentially means more effective isolation. There's a reduction in the tensile stresses. There is also a little bit more energy dissipation in these devices compared to conventional steel reinforced elastomeric isolators. And that energy dissipation is coming from the fiber itself. As you distort these bearings, as you deform them, there is the sliding that happens in the carbon fiber weave. And the sliding that happens there introduces an energy, a friction-based energy dissipation or damping. So, but there are challenges, of course. That's why we're here, okay, to research. One of the challenges is that their behavior, their mechanical behavior is becoming quite a bit more involved. And the existing models are not capable to capture that behavior very well. Okay? Especially when it comes to displacements under different levels of excitation. The other thing is that until recently, there wasn't much in terms of validation of these devices, especially at the system level. And then the problem of the stability of FREIs, both under zero lateral offset and under large lateral deformation is vastly unexplored. Okay, so what I'm going to be focusing on today is tackling some of these things that we've been investigating along these three areas. Okay, so first I'm going to talk a little bit about the dynamic modeling of 5 FREIs at multiple lateral deformation levels. Again, this is the backbone behavior over here. Okay, so you deform the bearing under, let's say, neglecting the dynamic effects here. So this is quasi-static behavior. There is a softening effect, and then you have full rollover, and there is a stiffening effect. Okay. Now, in terms of the dynamic behavior, here I'm showing you on the right force displacement loops for some cyclic tests that were conducted at different displacement levels. And there's a couple interesting observations you can make here. And those are that the energy dissipation per cycle increases as the displacement amplitude increases. Okay. And I'm not going to get into a lot of details about this aspect, but if you're using a natural rubber compound, the energy dissipation is essentially rate independent, but it's not linear, which is the typical assumption with displacement. It's something larger than linear. And the available models out there cannot really capture that. Okay. So, and the other thing here that is noteworthy is that the stiffness here, the unloading stiffness, is also a function of displacement. If you look at the stiffness, let's say over here versus here, that also varies with displacement. Okay, so the larger the displacement, the larger the unloading stiffness. So it's a little tricky to try to capture all these things. So what we wanted to do is to come up with a dynamic model that is able to actually capture these traits. And we followed the approach that others have followed. So that is to use a combination system. So we have a nonlinear elastic element in parallel with a hysteretic element. Okay. What is different in our approach is that our non-linear elastic element, which is supposed to capture the quasi-static behavior, is not based on some kind of curve fitting. This is what others have done so far. Okay? Take some data from test, curve fit it, come up with a polynomial, and use that. Ours is mechanics motivated. Okay? And I'll come back to the implications of using a mechanics motivated or what's the word used these days? Informed, okay, mechanics informed approach to using just an entirely data-driven method. The other thing is for a hysteretic element shown in the middle here, we wanted to be able to capture a higher than linear energy dissipation with increasing displacement. And when taking these two features together, come up with a model that is better able to capture what we see in experiments. Okay. All right, so let me talk a little bit about the nonlinear elastic element first. Okay, so first I'm dividing the behavior into two branches, what I call the pre-full rollover displacement, which is, again, full rollover is when when vertical face becomes horizontal, and then what happens after that point. Okay, so before contact, if you look at the force output of the element, that is given by, typical for an elastomeric bearing is GA over TR, that's your stiffness, times the displacement. Okay, in this case, this is G. This is an effective shear area. Okay, this is an A effective, and that is because that effective area reduces with displacement. Okay, so you have this element here that reduces it. And then if you take this and you break it up into two parts, essentially what you get is your linear component, but then you have the geometric stiffness component that reduces your force. After contact, what's been observed from experimental tests is that the behavior is fairly linear. Okay, so this equation here captures that kind of behavior. So what we can do then is take the behavior before contact, after contact, combine them into a single equation here using a soft heaviside function H. Okay, so that's for the quasi-static behavior. And then for the hysteretic element, here we're using a variant of the Bookwen model. Specifically, we're using a simplified version of the Baber-Wen model. And this one accounts for stiffness and strength degradation. But contrary to how it's used normally you use this for, say, reinforced concrete with increasing displacement, you get reduction in stiffness. In this case, we see something opposite to that. Okay, with increasing displacement, we see an increased stiffness, post-elastic stiffness, unloading stiffness. So this is a pivot-based Bookwen model, and maybe you have seen this before, maybe not, but beta, gamma, and N are parameters. I know some of you have seen it very much. So these parameters basically control the shape of the hysteresis loop. And then eta is a key parameter that relates the unloading stiffness to the initial stiffness. So this model tends to capture the behavior that we want, which is basically that the energy dissipation is not a linear function of displacement, but it's something larger than linear. Another interesting feature of this element is that if we set n equal to 1, okay, owing to Professor Haralabakis and Koumousis, there's a closed form solution for this. Okay, so that significantly reduces the computational cost rather than having to solve this in a state space setting. Okay, and also, I mean, we're not forcing it to make it more computationally efficient. Setting n equals to 1 actually agrees very well with experimental results. So this is a comparison of the predictions of 3 different models against experimental results. So the one in the middle is the model that we developed, and we called it the pivot Bookwen model, PBWM. On the left is a model developed by Vaiana at the University of Naples, Federico II. And then on the right is a model that my group developed earlier on. And here I'm comparing the behavior against experimental tests done both in the longitudinal direction in the first row and in the transverse direction in the second row. And what you can see is that the proposed model here is able to capture the behavior better than the others. But looking at hysteresis loops alone doesn't tell the whole story. So we wanted to also look a little bit at effective stiffness. Effective stiffness is something that is used, is a key parameter used in the preliminary design of seismically isolated structures. And then typically also effective damping ratio. But here we're not using effective damping ratio because effective damping is corrupted by the effective stiffness. So it's not a very good metric. So we're looking at effective stiffness on the left at different levels of displacement. Okay, it's normalized, but that doesn't matter here. And we're looking at a set of curves under longitudinal and under transverse direction. And what we see is that all models are able to capture the effective stiffness doesn't vary that much between the different models. They're kind of similar. Where the differences come is when you're looking at EDC, the energy dissipated per cycle, okay, over here to the left. And what you see here is, again, green is our proposed model, blue and red are existing models. And what you see is that the other models, the existing models, are not able to capture this trend that you observe with increasing displacement. Okay? In fact, what they do is they overpredict the energy dissipation at low displacements and they underpredict it at large displacements. Whereas the proposed model here is able to capture it, follow it fairly well. Now, what are the consequences of that? Who cares? Okay, so that's what we wanted to explore next. So we embarked on this case study, this investigation that involved response history analysis of a few different isolated structures. Okay, so we're looking at structures that vary from 1 to 4 stories, simple shear buildings, nothing fancy here. The isolation system is the same for all 4. Why? Because it has a period of 1.61, a little bit on the low end, but it's okay. For something like this, if you look at the nominal period of the superstructure, it would work pretty well. Okay, so we have these models, and then we use a suite of ground motions, ferry ground motions specifically. We scale them over this period range here, which is what is recommended by ASC 722. Okay, and we wanted to see what are the implications of using different models, different modeling approaches for the isolation systems while keeping all other things fixed. Okay, so what are the implications of our modeling assumptions? Okay, so first I'm going to focus on isolation layer displacements. Okay, on the top I'm looking at the behavior under what is called is MCR used in the European context or no?
I think this is just using a scale factor of 1.5.
1.5, yeah, that's the case in the US too. The difference between MCR and D is a factor of 1.5. And then the design earthquake used to be called the design basis earthquake. Okay, so I'm looking at displacements normalized by the total thickness of the rubber. So that's kind of like a shear strain for these devices. Okay, at these 2 different levels. And what we observe here is when we're looking at, let's look at the top graph here, is that the displacements that we're obtaining, the mean displacements, which is the black bars here, are larger than what the green again is the proposed model. So the responses obtained with the proposed model are larger than what we obtain with the other 2 existing models. Why does this happen? The effective stiffness is the same, okay? The EDC at these levels of displacement is actually supposed to be larger for the proposed model than the existing models. So how can the displacement be larger? It's because of the modeling assumption that we take in these existing models that basically overpredicts damping at low displacements and underpredicts it at large displacements. Because the isolation system tends to deform at relatively moderate levels, And there might be like 1 or 2 excursions that are very large. Overall, what you end up getting is a displacement that is larger, even though the effective stiffness is the same and the EDC at that target level of displacement is larger. It's because you have too much damping in the other models at low displacements. And then if you look at now the same thing, these normalized displacements at the D level, the increase in displacements is even larger. So for the top row, we're getting about 20 to 25% larger displacements when you're using the AEM. So that's the analytical model versus the proposed model. And then something in the order of 10 to 15% when using the PEM, pivot elastic model. And the situation becomes even worse at the DE level. Now, what are the consequences in terms of base shear? Okay. If you're looking at the design earthquake level, okay, we said we have larger displacements, so it would make sense that you would also have larger base shear. Okay, you see that agrees with what you see here. But when you're looking at the MCER level, you get base shears that are similar across the board. So what's happening here? Why does this occur?
Because the effective stiffness is evaluated for the largest earthquake, I think.
Well, what happens is that the stiffness that you use, the quasi-static model, okay, so the nonlinear elastic model, is obtained using regression, curve fitting, okay? And, you know, this is response history analysis. So you're gonna have some weaker earthquakes, some stronger earthquakes. And when you get to the stronger earthquakes, you end up getting some displacements that are larger than what you calibrated the model with. And because you're using a model that is based on a polynomial, typically of the 5th order, you get this very aggressive increase in force. And that very aggressive increase in force translates to these really large, these really large responses here. These are outliers. They're not real. These are just purely consequences of the modeling approach you're taking. Okay, so what you see here between the existing models and the proposed model is that you also get response that has a much smaller dispersion in the proposed model compared to the others. Now, how about floor spectra? So floor spectra are very important in the design of non-structural components. What happens here and how are modeling assumptions affecting the floor spectra? In an isolated structure, you get typically this large peak that is associated with the first mode, but it's not something to worry about because there are very few non-structural components that are that flexible. So you don't really worry so much about resonance at these large periods. Most non-structural components tend to be stiff, so they're in the short period range. And in the short period range here, you see these spikes that develop in the floor spectra. And those spikes tend to be right around the second mode, okay? When you're looking at the existing models, those spikes are accentuated compared to the proposed model, okay? And again, the reason is because you have all these extra unnecessary damping at low displacements. Professor Kelly earlier on noted that if you have large hysteretic damping in an isolated system, what that does is it decreases your isolation layer displacement, but all this happens at the expense of the superstructure response. Okay, you get larger drifts, you get larger floor accelerations, and you get larger spectral accelerations in your floor spectra at the short period range. Okay, now all these are consequences of the modeling approach. And it goes back to something Professor Konstantinidis at Buffalo has said again and again, that it's very important to develop highly accurate models of isolators in order to be able to capture what happens in the superstructure, if that's what you're interested in. Okay, so just some takeaways from the dynamic modeling study that we conducted here. We developed a phenomenological model for unbounded bearings. This model, the nonlinear elastic element of it is physically motivated. It's not based just purely on curve fitting. Unlike existing models, this model is able to capture energy dissipation over the entire range of displacements. And the proposed model predicts significantly larger isolation system displacement compared to existing models. That's important, okay? Because the stability of isolation system depends on those displacements. But also a nice feature of it is that it does not overestimate artificially in structural acceleration demands on non-structural components. Okay. Okay, I think I'm going a little bit slow here. So I'm going to try to speed up. What I want to talk a little bit about is validation of systems that use fiber-reinforced elastomeric isolators. Okay, until recently, there hadn't been a full-scale shake table study that explored these systems. So what I want to do is talk a little bit about this Ares funded project that we did at LNEC in Lisbon. And the PI for this was Daniele Lozano from University of Naples, Federico II. But several of us in the room were involved. Michalis, Dimitris, and I were part of the team investigating the systems. So essentially, this is a picture of a two-story full-scale building, well, 1 bay by 1 bay, full-scale, on the shake table at LNEC. Okay? And this is a picture of, well, what we tested. It had infill masonry in one direction. It had plaster boards in the other direction. And here are some of the details. I think I'm going to skip the input motion details, maybe focus a little bit on some of the results. We also outfitted this with some non-structural components. You can see a picture on the top right there, some cabinets, computer equipment, and so on. And we tested the structure using two different types of FREIs. We used, one was based on recycled rubber and using polyester fiber for the reinforcement. And the other is very much similar to what I've been discussing so far. So using virgin natural rubber and carbon fiber for the reinforcement. Now here's a test, video of a test that was done. And it's an isolated structure, not much is happening, which is what it should be, right? If you're in a base isolated structure during an earthquake, you should be bored. Okay? It shouldn't be exciting. Okay, that's the idea. But what happens is, to achieve that, all the action is happening at the isolation layer. Okay? So the isolators have to work hard in order to decouple the motion of the ground from the earthquake. So this is a fiber-reinforced elastomeric isolator, and you see, the kinds of deformation it experiences, the rollover, and the input here is triaxial. So this is a Kobe motion at 100%. And then I'm going to show you this particular bearing was the recycled rubber one. The next one is the virgin rubber and carbon fiber one. This is the strongest test we ran. So this is at 120% scale. Same motion. Extremely resilient devices considering their cost. We're talking about a few $100s. Okay. Now there's always concern about these things sliding and jumping and doing all kinds of things, and understandably so. Okay, because they're not bonded to the superstructure. So I mean that's something we looked at. And I mean, I'll give you some of our observations in a second. Now, looking at the superstructure response, I think the largest interstory drift we recorded was in the order of 0.5%. So that's pretty decent for a seismically isolated structure, significantly smaller than what you would have in a fixed base structure. In fact, I don't know if you guys know this, but they tested the fixed base configuration after our test a month later, and it did very poorly. And then here, looking at on the left, peak floor accelerations normalized by peak ground accelerations, you see that they tend to be in the order of 0.5 or less. Okay, so de-amplification in all cases. And then, so that's at the second floor level. And, oh, sorry, the one on the left is for the recycled rubber. The one on the right is for the virgin natural rubber. We see very, very good performance. So main observation from the shake table test, no structural damage was observed. Peak story drifts are in the order of 0.5% or less. Peak floor accelerations are less than 0.75 PGA. No visible damage to the non-structural components and contents. The masonry, infill walls and plasters, the stucco, everything was completely intact. There was a little bit of sliding observed for some of the desks, but very small, in the order of ½ centimeter. Then we tested two types of bearings. The recycled rubber bearings experienced no damage, but they had a little bit of distortion after the tests. Part of that distortion recovered after a day. The virgin natural rubber carbon fiber bearings had only superficial damage because as they were deforming, they came in contact with some sharp steel corners. But other than that, they did really well. There was no internal damage at all. Okay, so shifting gears, the last thing I want to talk a little bit about here is the stability of fiber reinforced elastomeric isolators. And what do I mean by stability? Well, because these are part of the load carrying system, they're essentially like columns, right? So you need to design, make sure that they are stable under dead and live loads. But also in an earthquake, you need to make sure that they are stable, they're very large deformations, while also being able to carry the weight of the superstructure. Okay. So I wanted to give you a little bit of context about the stability of conventional steel reinforced elastomeric isolators before talking about FREIs. But the approach that has been taken is to use a 1D beam element and to assume that there is shear deformation in the cross section. Okay, but there is no warping. Okay, so plane sections remain plane after deformation. An important assumption, which is basically based on the theory developed by Herrings, is that the axial force, the normal force P, acts perpendicular to the deformed section. Okay, it doesn't act along the elastic band, but perpendicular to the deformed section. And that gives a much more accurate prediction of buckling loads compared to the Engesser assumption. So using this theory, which is sometimes referred to as the Herrings theory, you can calculate the critical load, the buckling load for an elastomeric bearing. Now, an elastomeric bearing consists of layers of rubber and steel. Okay, it's not a homogeneous element, but there is a homogenization process that you can follow to kind of treat that composite as a homogeneous element. And after you do that, you can come up with the critical load as a function here on the right side. This is on the vertical axis is critical load normalized by the shear rigidity. On the horizontal axis is the ratio of flexural to shear rigidity. And you get a behavior like this. Now, is this accurate to use for fiber reinforced elastomeric isolators? Fiber reinforced elastomeric isolators use fiber, not steel shims, and fiber provides very little bending rigidity. Okay? It flexes, it warps. So you need something, you need a theory now that is able to account for that. Okay? And there have been some theories proposed out there, not in the context of rubber bearings, but in the context of beams. And they try to account for the warping deformations that you get at the cross-section level. Okay, here on the right, I'm showing some of the predictions of these theories. Harring's is the one I showed you before that does not consider warping. And then there are theories by Juan Simo, Kelly and Tsai, and Chalamel for that do try to account for warping. But what you can see here in this range of flexural to shear rigidity, which applies to elastomeric isolators, typically in the range of 200 to 1,000, maybe up to 10,000, the predictions are all over the place. Okay, there's nothing close to consistency here. Okay. Another thing is that these theories have been developed for the planar case, not for the case of a 3D element, which is really what we want. And they're not easily extendable to the 3D case. Also, there is no experimental validation for them. So we set out to try to come up with something new now. For the time being, what people assume in the absence of a better theory is that Harring's theory is appropriate for fiber reinforced elastomeric isolators. Is it? I will come back to that. Okay, but what we wanted to do here is to develop a theory that enables to develop closed form solutions for the critical load of these bearings, of fiber reinforced elastomeric isolators. But we also wanted to bypass some of the issues that I mentioned. So the approach was to treat the bearing as a 1D element, because that's really what we can handle analytically. But to start with using a 1D rod rather than a beam. So essentially the difference here is that when you develop beam theories, there are some underlying simplifying assumptions about the deformations or the displacements or the rotations. Typically one or more of these is small, okay? And that allows you to come up with a relatively simple formulation. A rod doesn't have any such limitations, so it can be much more general. And that's what we wanted to start with, okay? Here I'm showing you the deformation field associated with the with a 1D rod over here. And this component here is really what is key in terms of the warping deformations at the cross-sectional level. We have a warping function W, and we have an amplitude function alpha that is associated with that. And so we take this as our departing point, and we want to basically expand on the virtual work to determine the work conjugate strains. So the strains that thermodynamically consistent with our choice of stresses. And what are our choice of stresses here? We're using the normal stress sigma and the tangential stress tau in the deformed configuration. Okay. So once we derive these strains, which are shown here, and these are clearly strains that are measures of large deformation. Then the next step is, once we have these strains, to make some assumption in terms of the constitution of the material. So how are the stresses related to the to the strains. And their assumption we're making here is that they are linear. So this is the sigma and the tau. They are linear with respect to these strains. But again, these strains are large deformation strains. Okay. Now, once you have these, stuck again. Okay. Okay, so once we have this, we can proceed using a stability criterion to come up with the critical load for these devices. So essentially what we're doing is we're taking the linearization of the virtual work relative to the equilibrium configuration of the rod. And we're doing it here to start with under pure compression, okay? No lateral offset. And essentially what we're trying to do is we take that, we set it equal to 0. That essentially gives us the condition under which the stiffness becomes 0, okay? Basically when the equilibrium bifurcates. So once we do that, and of course here I'm skipping a lot of algebra, a lot of math, we come up with this equation here, okay, for P bar. P bar is a normalized load. And if you solve this equation, which is a quartic equation, you can determine the P critical. That's nice, okay? But as a practicing engineer, I want to use something like this. This is a quartic equation, it requires iterations. And the other thing that I didn't mention is that embedded in this equation are 4 warping functions or working parameters that you have to compute through integration. It's quite involved. Okay? So it's not something a practitioner wants to do. So what we wanted to do is explore whether there is a simpler equation that we can come up with. And we did. Basically, we looked at this equation. We investigated its behavior under different parameters. And what we saw here is that for large values of flexural to shear rigidity, which is really what applies to elastomeric isolators, and for large values of axial rigidity to shear rigidity, so basically in this range, the solution basically sort of asymptote some closed form solution. And so that closed form solution is basically an approximate solution is this, okay? Now, the beauty of that equation is that you can take that and you can actually compare it against Harring's solution. Harring's solution, again, does not account for warping, okay? But if you see these two, if you compare them, so this one accounts for warping, this one doesn't. And the difference is this denominator here. This denominator that introduces these two parameters, FB and EJ, which are associated with the warping of the cross section. Okay, so this is a nice way of actually linking the existing theory out there, which I will show you in a second is quite erroneous to use, with this new theory that takes into account the warping. Now, there's one more step here that we need to do, because what I've done so far is discuss the case of a homogeneous element. But as I said before, a rubber bearing is not homogeneous. It consists of layers of rubber and reinforcement. So there needs to be some kind of homogenization process. And such a thing has been done before in the case of coming up with effective axial rigidity, effective bending rigidity for rubber bearings. And the idea here was to extend this theory and to come up with effective warping rigidities for this new formulation. To achieve that, basically, the approach is to apply a so-called pressure solution that's been used widely. And it's based on some assumptions regarding kinematics and the stresses, and also uses infinitesimal strains. But the beauty of it is that you go from a three-dimensional problem to a two-dimensional problem where you have a pressure here that is only a function of what happens at a cross section. And basically now you need to solve this equation here, this PDE. W is the warping function on the right-hand side. It's a little tricky, but it's tangible. You can solve it numerically, but you can also solve it analytically with some effort. Okay, so the idea then is once you get these pressures, you take the pressure distributions and you use them in these equations to determine your effective warping rigidity and this other parameter FP. Okay, once you have those, you go back to your P critical equation from the previous slide and calculate your buckling load. Now, is this theory an improvement? Okay, so what we did here was we compare the predictions of our theory against the predictions of some very high fidelity FEA results that we have. We've been doing FEA of rubber bearings for many years. We've acquired quite a bit of expertise over that. So we consider those sort of our benchmarks, and we wanted to compare against them using this new theory. And we did it for different geometries of bearings: square, circular, and annular. Annular is basically a circular bearing that has a hole in the bearing. Okay? And on the horizontal axis, you have the shape factor, which is a parameter that basically tells you, it basically describes the thinness of a rubber layer in a rubber bearing. And then on the vertical axis, it's kind of like an aspect ratio, a width to height aspect ratio. And what you see here is that typically for fiber reinforced elastomeric bearings, the shape factor, which would be in the order of maybe 15 or so. Okay. And what you see here is that around this neighborhood, the predictions of our theory is really, really good. All geometric shapes, and maybe deviates by maybe 5% at most. Okay, and so that's what this ratio here, this is the ratio of the analytical solution that we derived versus the P critical obtained by finite element analysis. So a value of 1 basically indicates that it's right on, and anything other than that is it's a little different. How about existing theories? Well, what theory? Harriks's theory. Let's see what Harriks's theory predicts versus the FEA analysis. So different shapes again, square, circular, and annular. And what you get here around this neighborhood of 15 or so is that the prediction, you see this factor here, can be as little as 1.5 or 1.75, all the way up to 2.8 or 3. Okay. Now look at this ratio here. Okay. That on the numerator is the analytical prediction. On the denominator is the FEA. So this is your benchmark. So these are unconservative predictions, right? And the key point here is that it is critical when you're calculating the buckling load of fiber reinforced elastomeric bearings to consider warping. Okay. Okay. I'm gonna fly over some slides here because we're out of time, I think. The next step here was to consider the coupled behavior of lateral and vertical. Seismically isolated devices or seismic isolation devices are supposed to experience very large deformations. How is the stability of these devices affected by those deformations? And what we wanted to do is not just look at fiber reinforced elastomeric isolators, but we wanted to go back and revisit this assumption that's been floating around since the inception of steel reinforced elastomeric isolators, that the steel is rigid. Is it really rigid? We wanted to go back and look at that. So I don't have time to go over this, and maybe it's okay because this hasn't been published yet. But the idea is we wanted to extend our theory. The mathematics and the computational effort becomes very, very large. So we took a slightly different approach here, a multi-scale approach, where we have a structural element over here representing the isolator. But then within that structural element, this is a macro scale model. We have a mesoscale model, which is a unit cell, where we try to capture the mechanics of what happens there. Now, ultimately, the goal is to come up with a model that can be used in response history analysis, linear response history analysis. But the computational effort involved in the mesoscale unit cell is really, really quite involved still. So you cannot do it on the fly in real time. So the idea then here was to come up with a model that is able to, a surrogate model, where we do a lot of analysis offline. We come up with a solution space and then have that offline database that we can use to train the model to come up with predictions of the behavior of that unit cell. Skip the math here. And this is about the training of the model. But essentially, let me show you just a couple of results here. So this is now trying to compute, and this is going back to the idea where we also want to test the assumption that's been floating around about conventional steel reinforced elastomeric isolators. So this is a bearing under compressive load, and we're considering a lateral perturbation. So this is a very, very small fraction of this. And basically what happens is you apply some loading and then suddenly the bearing buckles. And you see that our prediction, which is this multi-scale with warping, solid line, closely aligns with the predictions of the benchmark finite element analysis. Okay? If we don't consider warping in our multi-scale approach, looking at this, then we're really overshooting the critical load. And then together with this, I've also included the sort of state-of-the-art model that's been out there by Kumar and Konstantinidis. And you see that this is also not able to capture accurately. It really overpredicts the buckling load. So it's highly conservative. Now, a couple scenarios here. Now, this is the case where I'm considering both lateral deformation and vertical load. And I'm considering two different vertical loads now, keeping this ratio P to P critical to 0.3 and then 0.7. And what you see is that for lighter loads, 0.3, then all the models are able to capture the behavior fairly okay. But once you get to large critical loads, and in a dynamic analysis, you can't get to large critical loads. It's not just your nominal, your service level loads. Fluctuation in the axial loads in the columns can result in large P's. So what happens here is that you see that the predictions of the existing models can become fairly poor, whereas the predictions of the model that we just developed, solid line red, closely aligns with the predictions of the finite element analysis. Okay, and what are we doing next? We're doing tests, okay? This is all beautiful, but without experiments, we can't really validate it. So the next step is to do some component level testing to see what the behavior of the devices is at the component level, to be able to validate and calibrate our models. But also we're going to do some shake table tests because we want to see what happens at the system level. Like, okay, maybe one bearing buckles, becomes unstable. What happens to the system? Does the system become unstable? So we want to kind of explore these things. So we're going to be doing this over the next few months at Berkeley, at the Pacific Earthquake Engineering Research Center, shake table there. Okay, so I think that's it. Ongoing and future inquiries. We're still working on stability of FREIs. We're looking for ways to reduce lateral stiffness, basically increasing the seismic isolation efficiency. We want to see how high we can actually go. Again, these bearings are not bonded to the top and the bottom. So, at some point, of course, you're going to have issues with uplift. So when does that happen? The test we did at LNEC, we went to, if I remember correctly, the PGA in the vertical was 0.6, something like that. So, yeah. And I mean, you're not just concerned about jumping, but you're concerned about the fact that you have friction. So as the normal pressure becomes lower, you're concerned about sliding. But rubber is an incredible material. It doesn't abide by Coulomb friction. There's a lot more friction there than Coulomb predicts. Then we're interested in looking at the behavior of these devices and structures using the devices under extremely large earthquakes. And last but probably the most important thing, implementation in practice. Okay? There's quite a bit to be done before we get there with confidence, but we're hoping to be there at some point. The last thing I just want to do is acknowledge my PhD. So these are pictures of my students at Berkeley, past and current. But the person who has been the most instrumental in the work I presented today is Eduardo Montaldo. So I wanted to acknowledge his work. Eduardo has accepted a position at University of Colorado Boulder. He's going to be starting there in January. Okay, I'm sorry for going a little bit over time. I'm going to stop here and see if you have any questions.
I have to start with it. How does that buckle bearing look like? Does it look very stocky? So I can't really picture it.
It doesn't deform very much in the vertical direction, but it just goes like this and then it starts moving to the side. And I mean, we have done finite element analysis where you actually can visualize that. I can send you some pictures. Buckle bearings, not fiber, but conventional bearings that are bonded top and bottom have this very peculiar theoretical behavior Michalis knows about because he studied them during his master's at Berkeley. And that is that theoretically, they can buckle under tensile loading. Theoretically. In practice, you get other issues. You get cavitation with the rubber. You get things that happens and so on.
Questions from the audience, please. Guys, that we have.
Μπορεί να απαντήσω στα αγγλικά.
Είναι σχετικά ταξιτούς. Επειδή βλέπω ότι αυτό το fiber τώρα το αλλά φαίνεται ότι τρώει περισσότερη παραμόρφωση. Δεν τρώγεται το υλικό πιο γρήγορα.
Όχι απαραίτητα. Η παραμόρφωση που νιώθει δεν είναι τόσο μεγάλη. Καταρχάς η παραμόρφωση under service level conditions που λέμε είναι πολύ μικρή. Τώρα, κατά τη διάρκεια ενός σεισμού, νομίζω ότι τα deformations είναι σχετικά παρόμοια μεταξύ fiber reinforced, unbonded, fiber reinforced και bonded, steel reinforced.
Ο μέσος χρόνος ζωής του συστήματος
είναι μεγαλύτερο. Νομίζω είναι πολύ μεγαλύτερος από ότι ο χρόνος της κατασκευής. Δηλαδή υπάρχουν κάποιες γέφυρες για τρένα που είχαν χτιστεί στην Αγγλία πριν από 90 χρόνια, χρησιμοποιώντας ελαστικά που ακόμα είναι σε πολύ καλή κατάσταση. Και σε κάποια στιγμή είχαν αφαιρέσει ένα από αυτά τα εφέδρανα, το κόψανε στη μέση και αυτό που παρατηρήσαν ότι υπήρχε κάποια διάβρωση στα άκρα, αλλά το εσωτερικό ήταν όπως ακριβώς, intact.
Δεν τους το νόμιζα παλιό να τα λάστιχα των αυτοκινήτων. Νόμιζα παλιό να τα λάστιχα των αυτοκινήτων.
Τα λάστιχα των αυτοκινήτων δεν είναι natural rubber, είναι synthetic rubber και έχουν πολύ χαμηλότερο lifespan. 5 χρόνια, νομίζω είναι το rated. Από κάποιο σημείο και μετά αρχίζουν και σκάνε. Αλλά έχουν άλλα χαρακτηριστικά που κάνουν έτσι attractive.
Are there any re-centering issues after a major event? Because we saw this video with Kobe earthquake that there was torsion of the main structure.
I would say there are actually less of an issue with recentering with these bearings than there is with conventional bearings. The typical rubber isolation system is the lead rubber bearing system.
Yeah.
And the lead rubber bearing system has a lead core.
Yeah.
And the lead core is basically a hysteretic element. Yeah, so at the end of an earthquake, you can have some plastic deformation, residual plastic deformation that you know, maybe sometimes you recover a little bit with aftershocks, but theoretically it could be there.
Okay. And one question about the models that you used in the first part of the presentation. Apart of the hysteretic one, the other two just overestimate the damping of the isolator. That is why they have smaller displacement than the hysteretic.
Those also have a hysteretic element. Yeah, they do. They have the same structure. So you have a nonlinear elastic element in parallel with a hysteretic element. So those have one too. It's just that the one that they're using is not really capturing.
But the green one had experienced greater values of displacement than the red one and the blue one.
Yes. And it goes back to having too much damping.
So the damping is less in this system in order to have larger displacements. So
First of all, the damping in the proposed model is more accurate in terms of the fact that you have less damping at low displacements and larger damping at higher displacements. Whereas the existing models are the opposite. I mean, they're basically linear with displacement, which is not really what we've seen from experiments. But it is what is commonly used for hysteretic damping. You have just a linear variation with displacement.
Okay. And this point with nodes, this hysteretic model, it's something common. This points, these two nodes that
The pivot will.
The pivot, yes.
It's a hammer.
It's based on Parks, I think they call it Parks law. Where you have a pivot point, and this is actually a problem in during hysteresis because for the reinforced concrete case, it predicts stiffening if the experiment is the opposite. Yeah.
So there's a point parameter that guides these
the
points.
position of these points.
Yeah.
But this is calibrated.
This is calibrated.
Calibrated
Experimental,
for-
yes. Yes.
Experimental.
Yes, this is a phenomenological model. It is inspired by mechanics, but you still need to have some kind of experimental results to calibrate, especially the hysteretic part of it. So the idea behind this pulse is that basically when you get this unloading behavior, everything is kind of, if you extend these unloading branches, they go through that point. Yes.
Δεν υπάρχει εμπορική εφαρμογή.
Υπάρχει κάποια στον Καναδά. Είναι μια γέφυρα στο Οντάριο που έχει χτιστεί και χρησιμοποιεί fiber reinforced elastomeric isolators. Αλλά η εφαρμογή εκεί δεν είναι τόσο για σεισμική μόνωση. Είναι για thermal expansion και contraction.
Περισσότερες γέφυρες. Αν ο τρόπος θα επιστηρίζει, είναι ιδιότητες εξαρτώνται.
Τυποποιημένος δεν είναι, γιατί είναι ακόμα στο research level.
Δηλαδή, αυτό το fiber mesh δεν το παίρνει μέσα.
Αυτό οι εταιρείες έχουν κάποιο know-how για το πώς να γίνει. Όχι όλες, αλλά οι καλές. Η Μακέβα, για παράδειγμα, η Good Go στον Καναδά, που ξέρεις είναι λίγο πιο... που έχουν μεγαλύτερο knowledge base για το πώς να κατασκευάζουν εφέδρανα. Υπάρχουν και πολλές εταιρείες που φτιάχνουν εφέδρανα που, εντάξει, απλά τα φτιάχνουν. Εκεί είναι λίγο ανησυχητικά τα πράγματα. Όχι. Πολύ λίγες. Είναι ακόμα στο ερευνητικό στάδιο.
Δεν σου σκέφτομαι ότι είναι πολύ καλό. Σκέφτομαι να το κατασκευάσουμε.
Είναι κάποιες, ακόμα και στην Ιταλία, η Talgam, που μας έφτιαξε αυτά τα εφέδρανα που χρησιμοποιήσαμε στα Sig Table Tests, που τα κάνουν πάρα πολύ καλά. Εντάξει, τώρα το process αυτό είναι proprietary, αλλά εντάξει, νομίζω είναι θέμα χρόνου μέχρι να αρχίσω και άλλες εταιρείες να τα φτιάχνουν σωστά. Το rubber compounding είναι κάπως σαν κατσαρόλα, ναι. Όχι ακριβώς, αλλά ναι, είναι πολύ... Είναι λίγο σαν μαγειρική. Μιχάλη.
Είναι φόρμα που είναι ο μέσος που έχει 20 χρόνια. Μετά σε ουσία που είχε το σπιτιό, έχουν γίνει πάρα πολλά παραπάνω πράγματα που έχουν γίνει και καλά στις δεκαετίες όταν ήταν στην Ανατολή. Δηλαδή, τι παραπάνω είναι να πούνται τελικά για να φτάσει στην Ανατολή. Δηλαδή, κάτι στην κανονίση που σου κάνει, και είχαν και πολύ δουλειά, η ιδιωτική μαγεία που ακούει, ξέρω να φτιάξουν, αλλά δεν κάνουν συνδυασμό. Γιατί πουλάνε άλλα, αυτά δεν είναι πολύ καθημερινά, είναι γιατί κάπως έτσι δεν είναι από αυτά. Οι Κινέζοι μου γίνεται πάλι θα σε φιλούς. Όχι ποτέ και μας. Και ξαναφτιάχνω πολύ φιλότερο, και το ξεπέρι. Καμιά ιδέα πώς να το προχτεί αυτό.
Είναι δεμένη. Η εμπειρία της foundation, είναι άορας. Δεν είναι η καλύτερη. Η εμπειρία που έχει επηρεάσει. Δηλαδή, δεν υπάρχουν ψάχνει τα χέρια που βάλεις tower laminated particles. Όπου και είναι πώς να είναι τα δύο. Αυτό είναι σίγουρα στην πλέον πειράσει. Παίρνει
Νομίζω σε developed world applications είναι αρκετά πιο δύσκολο να τα πουλήσεις αυτά. Εκτός αν είναι και καλά για... Δηλαδή δεν θα αντικαταστήσουν ποτέ τα LED rubber bearings ή τα high damping rubber bearings σε σημαντικές κατασκευές. Αλλά το θέμα είναι να κάνουμε expand το seismic isolation. Γιατί ακόμα και για ordinary κατασκευές, το κόστος αυτών των bearings είναι πολύ χαμηλότερο. Και μετά σε developing world applications, τα conventional bearings, εντάξει, δεν μπορείς να τα χρησιμοποιήσεις καθόλου. Αν το ένα bearing έχει 10.000, εντάξει, και αν φτιαχτούν στην Κίνα και πάλι θα έχουν, ξέρω, 2.000 μπορεί.
Πώς υπάρχει ένα κινέζικο bearing?
Ότι δουλεύουν. Δηλαδή, κάναμε και τα πειράματα και είδαμε ότι δουλεύουν, αλλά υπάρχουν κάποια πράγματα που πρέπει να μελετήσουμε πριν τα...
Πάρεις παραγγείλα σκυλί, πες τι έλεγα από το 1929. Τούτα μακρονίες μια καθόλου χρόνια, αυτή που έλεγε στην Επιτροπή, τους πάω. Δεν τα έλεγε. Και στους Γερμανούς που μας λένε να κάνουν συζητημό στην Ελλάδα. Έγινε αντίστοιχα στην Αμερική.
Όχι, στην Αμερική δεν έχουμε κάτι αντίστοιχο, γιατί εκεί τα projects είναι συνήθως με peer evaluation. Δεν είναι τόσο standardized, δηλαδή το κάθε project περνάει από... Υπάρχει ένα peer evaluation group και δηλαδή μπορείς να χρησιμοποιήσεις άλλα εναλλακτικά εφέδρανα, αρκεί να έχουν μελετηθεί από experts. Δεν είναι τόσο standardized όπως στην Ευρώπη. Όχι, τα code committees στην Αμερική είναι practitioners, manufacturers. Εντάξει, και στην Αμερική, σε αυτά τα committee, γιατί είμαι στο committee της ASC7, στο task committee για isolation, και υπάρχουν όντως άτομα που είναι από την EPS, Earthquake Protective Systems, γελάει ο Δημήτρης.
Τώρα πάω στο Ζάγια κάτι και μιλάμε με πήρε τηλέφωνο κατευθείαν και τα χώνεται.
Υπάρχουν άτομα από την DIS που φτιάχνει τα LED rubber bearings, αλλά, ναι, ανάμεσα στο committee, αλλά δεν είναι μόνο αυτοί, υπάρχουν και πολλοί άλλοι practice από την ακαδημαϊκή κοινότητα, καμιά φορά και από government regulators, ειδικά στα nuclear committees, πάντα υπάρχουν αντιπρόσωποι από τα regulation body. Και άλλες ερωτήσεις.
Στα fiber, συνδυότητες του όλου του συστήματος. Τι έχουμε στις
Δεν το έχουμε μελετήσει αυτό. Δεν ξέρω να σας απαντήσω με σιγουριά. Θερμοκρασία σκεφτόσαστε δηλαδή ambient conditions ή...
Στα 50 βαθμούς το καλοκαίρι, εκεί δεν θα έχουμε αυτή τη ιδιότητα του μοντέλου.
Εντάξει, τέτοιες θερμοκρασίες μπορεί να αλλάζουν και την απόκριση του ελαστικού. Και αν έχει sliding bearings και εκεί ακόμα και το συντελεστή τριβής. Δηλαδή πάντα υπάρχει κάποια... Αλλά δεν το έχουμε κάνει quantify. Νομίζω περισσότερο πρόβλημα είναι οι κρύες θερμοκρασίες. Είναι κάποιοι ερευνητές στην Ινδία που μελετάνε αυτή τη στιγμή το effect του temperature.
Τη στιγμή που δουλεύει ανεβαίνει μέσα.
Στα natural rubber bearings ανεβαίνει λίγο. Στα high damping rubber bearings, επειδή έχουν διάφορα additives, carbon black, διάφορα resins, για να ανεβάζουν το damping, εκεί ανεβαίνει η θερμοκρασία λίγο. Οι Ιταλοί έχουν χρησιμοποιήσει και natural. Τα neoprene είναι synthetic. Ναι, συγκεκριμένα synthetic rubbers όπως το neoprene είναι στάνταρ στα εφέδρανα, στις γέφυρες. Επειδή έχουν πολύ καλό environmental resistance. Δηλαδή χρησιμοποιούνται περισσότερο και από τα natural rubber bands. Αλλά συγκεκριμένα για σεισμική μόνωση, τα χαρακτηριστικά του natural rubber είναι καλύτερα από το neoprene. Γι' αυτό τα προτιμάμε. Ναι.
Για τη στήριξη της βάσης του προγράμματος τύπου, δηλαδή, από το πρώτο περίπτωση,
ναι, δεν πρέπει να την κάνεις block κάπως, να είναι... Όχι, δεν χρειάζεται. Αυτό που μπορείς να κάνεις είναι να κάνεις λίγο treat την επιφάνεια, να την κάνεις πιο άγρια, αν θες να ανεβάσεις το συντελεστή τριβής. Αλλά ναι, νομίζω ότι δεν προβλέπεται να κάνεις κάτι ιδιαίτερο.
Αν δεν έχει κάποιος άλλος,
Σπρέι που δουλεύουν στα συνέπειες σχετικά λίμνης ουσίες για τις σπρέις.
Στα conventional, στην Ιαπωνία πας μέχρι και 400%. Στην Αμερική το πολύ 300 θα έλεγα. Τα συγκεκριμένα εδώ πάνε μέχρι 200 κάτι, γιατί από κάποιο σημείο και μετά η κάθετη επιφάνεια γίνεται οριζόντια. Όχι. Νομίζω το ότι από κάποιο σημείο και μετά γίνονται σαν μπάλα, τα βοηθάει, να προστατεύει από να... Είναι γύρω στο 200-225% equivalent shear strain. Δεν είναι πάρα πολύ μεγάλα. Ναι, σου λέω για γάμα.
20.000 στα ίσως να μπορεί να πάρει περισσότερο. 20.000 ίσως περισσότερο. Οπότε, οι συνεγγυρίες.
Αυτό είναι κυρίως το κόστος, αλλά το κοιτάξαμε κιόλας σε αυτά τα πειράματα. Μισό λεπτό να σου δείξω. Αυτά τα πειράματα που κάναμε κάναμε στο LNEC. Κοιτάξαμε δύο configurations. Το ένα είναι που τα bearings δεν έχουν καθόλου restrainers πάνω και κάτω. Είναι αυτό που βλέπεις εδώ. Και το δεύτερο είναι... Εδώ έχει αυτό το restrainer που είναι σαν μια μεταλλική... Δεν είναι κολλημένο. Ναι, αλλά δεν τα επιστρέψει δεν τα επιτρέπει να γλιστρήσουν.
είναι χωρίς το λάμι της ενδιάμεσης, γιατί αυτό το παίρνει, δεν έχει λάμι.
Δεν ξέρω αν αυτό είναι φάρμακο. Νομίζω δεν είναι καλό να το κάνεις αυτό, γιατί μετά, άμα τα κολλήσεις, θα κυνηγάς την ουρά σου, γιατί θα ανεβούν τα tensile stresses και μπορεί να κάνουν την bond μετά μεταξύ του rubber και του fiber. Αυτό το πρόβλημα το έχουν τα laminated rubber bearings, αλλά εμείς θέλουμε να το αποφύγουμε αυτό το πρόβλημα. Γιατί είναι πολύ ακριβό να τα κάνεις bond.
Θα βοηθούσε να βρουν application. Εσείς το πλητό, όλο αυτό το κάνει για να μπουν. Δεν ξέρω. Σε αυτή την περίπτωση, μόνο με τους έρευνες. Δεν έχεις ξεκαθαρίσει την επικοινωνία. Δεν είναι. Δηλαδή, εσύ εδώ πέρα έχεις ένα solid block, το οποίο θα το κολλήσεις πάνω από κάτω. Δεν έχεις να κολλήσεις κάθε layer πάνω στο λάμινι.
Μα τα layers είναι bonded μεταξύ τους, το rubber και το fiber είναι bonded. Άμα τα κολλήσεις πάνω και κάτω και τα κάνεις shear, μετά θα έχει μεγάλα tensile stresses που μπορεί να κάνουν debonding μεταξύ των κολλημένων rubber και fiber.
Το fiber θα το debonding, γιατί δεν γίνεται να τους κάνεις τα λάμινι.
Να σας διακόψω λίγο τώρα, γιατί έχουμε εξηγήσει πολύ τεχνικά θέματα. Και να χάσουμε το κοινό μας. Αν δεν σε ρωτά αν υπάρχει εξαντλητέριο, δεν υπάρχει κάποιος θέλει κάτι από εκεί. Τους ξεχάσαμε. Ρώτα, γιατί δεν έγραψαν κάτι από ερώτηση.
Οκ. Είναι κάποιος στο κοινό online που έχει κάποια ερώτηση? Any questions from the audience online?
Οκ, super. Οπότε να σας απελευθερώσω, να σας ευχαριστώ. Εδώ είναι ο κ. Konstantinidis. Επιτεθείτε ελεύθερα. Πριν προλάβει να πάει το